Today we're going to do lesson 6 of the applying genetics problems. Question 1 says Niemann-Pick disease is a rare genetic disease inherited in an autosomal recessive fashion. The non-disease allele is capital D, while the Niemann-Pick disease allele is lowercase d. Suppose that the Niemann-Pick disease affects 1 out of 150,000 individuals in a certain population. In all cases, parts A through D, please indicate your answer to 4 decimal places. So for part A, it says what is the frequency of the lowercase d allele in this population, so the disease allele. So what we're going to do here is find the frequency. So it says that the Niemann-Pick disease affects 1 out of 150,000. So that's how we find that frequency, that ratio, with 1 out of 150,000. So if we calculate that, it gives us a really small number. 1, 2, 3, 4, 5 zeros, 3 sixes, and a 7. And that is equal to the 2 a's or the q squared. So to find the frequency of that, we need to take the square root of it. So if we take the square root of this number here, it will give us this number. Or 2.58 times 10 to the negative 3. And that is equal to Q. Part B says what is the frequency of the capital D allele in this population? To find that number, we take 1 minus Q to find our P. So 1 minus Q, is equal to P. Or 1 minus this number, 2.58 times 10 to the negative 3 equals our P, or 9.97 times 10 to the negative 1. Part C says what is the frequency of the capital D genotype in this population? To find that number, we need to find P squared. So if this is P, if this number is our P, we just need to square that number to find the genotype of capital D. So if we square that number, 9.97 times 10 to the negative 1 squared, that will equal 9.95 times 10 to the negative 1, or P squared, or DG. Part D says what is the frequency of the capital D lowercase d genotype, or the heterozygous genotype in the population? To find that, we do 2 times P times Q. So we take 2 times our P value times our Q value. So it would be 2 times 9.97 times 10 to the negative 1 times 2.58 times 10 to the negative 3 equals 5.15 times 10 to the negative 3. And that would be our answers for A, B, C, and D of question 1. Now, for question 2, it's fill in the blank. So I'm just going to go ahead and read each definition with the answers. A says the term in the Hardy-Weinberg equation that represents the frequency of the IB allele is Q, while the term in the Hardy-Weinberg equation that represents the frequency of the IA-IB genotype is 2PQ. B says DeGeorge syndrome is an autosomal dominant disorder that affects 1 in 4,000 individuals in the human population. The 1 in 4,000 individuals in the population affected by DeGeorge syndrome is represented by the P squared and 2PQ terms in the Hardy-Weinberg equation. C, this equation refers to the situation represented in part B. The 3,999 of 4,000 individuals is the population unaffected by DeGeorge syndrome is represented by the Q squared terms in the Hardy-Weinberg equation.
All right, so the next part, so part D, asks us about, I'll just go ahead and read the question. It says the type of plumage found in mallard ducks is determined by 3 alleles at a single locus. MR produces restricted plumage, M produces mallard plumage, and MD produces dusky plumage. The restricted phenotype is dominant over mallard and dusky. Mallard is dominant over Dusky, and the R term is in the Hardy-Weinberg equation, best represents the frequency of the MD since it's recessive. E, this question refers to the situation presented at D. The MR, MR, MRN, and MRM terms in the. Let me just back up a little bit. So, M big R, and then M, and then M, and then M big R M. So that's going to give us the genotype of the restrict. And then I'm going to turn it over to Carly for
All right.
the next few questions.
Okay. So this is for F. The human disease sickle cell anemia is a result of a SNP. For G, the answer is monomorphism, and that's a term that describes a trait that produces a single phenotype in 99% or more of the population. H is DEEM, is another name for a local population, and the last one is I. It says the MHC genes in humans are highly polymorphic. Okay. So moving on to question number 3. The question asks, Marfan syndrome is an autosomal dominant disorder. For the purposes of this problem, we will assume that Marfan syndrome affects 1 in 6,000 individuals in the human population. So for part A, it's asking what is the frequency of the non-disease allele in the human population? Indicate the answer to 5 decimal places. So this one's going to be pretty similar to the problem that James just showed you. You're going to use the Hardy-Weinberg again. So for the first one, we know that 1 in 6,000 people are affected by it. So to determine the amount of the people that don't have the disease, we're going to take the remaining amount, which is 5,999, and divide that by 6,000. And so that gives you, well, that's going to give you the recessive allele. And so once you have that, you know that that's equal to Q squared. So you take the square root of 5,999 divided by 6,000, and you figure out that Q is equal to 0.9992. And that's the frequency for the non-disease allele. So for part B, what is the frequency of the Marfan syndrome allele in the human population? We know that P plus Q equals 1. So we have Q, and so what we're going to do is 1 minus Q. So 1 minus 0.9992, and that is going to give us P. So that's going to give us the frequency of the Marfan syndrome allele. And the answer for that one is 8.33 times 10 to the negative 5. Okay. And so for C, what is the frequency of heterozygous individuals in the population? So in the Hardy-Weinberg equation, 2PQ tells us the frequency of the heterozygotes. And so we just have to multiply our previous 2 answers by 2. And when we do that, we get that the answer is 1.666 times 10 to the negative 4. Okay, and for the last one for D, it asks, out of a population of 5 million people, how many heterozygotes are expected? So there's an equation, and it's allele frequency is equal to the number of copies of the allele that you're looking at. So we're looking at the heterozygous allele, divided by the total number of alleles in the population. So to solve this one, we know that there are 1.66, so this is D, there are 1.666 times 10 to the negative 4% of people are heterozygous. And so we set that equal to X over the total amount of alleles in the population, which is 5 million. And then we figure out that that 833 people are expected to be heterozygotes.
All right, so just a quick correction on question 2. So the correct answer, I referred to the actual genotypes. It should be P squared and 2PQ since it's referring to the dominant and the heterozygote. So just a quick correction on question 2, part E, I believe. For the next one, we're going to run through a situation where the Hardy-Weinberg equation is used to find a chi-squared value. Scroll down on this computer. Okay, I have it on my notes. So what we're going to find here, since this equation is a little different, since we're finding we have 3 genotypes, and each of the alleles, it doesn't go over in a complete dominant fashion. So we're going to need to find the allele frequencies all separately. So our number observed is 135. So up here we have 2 of those alleles, so we're going to multiply it by 2, and that's going to give us a number. And then we are going to, so then we have for the next genotype, for the next number genotype observed, we have 44 for the r squared, so we'll make this r squared, and then this r3. And then we also have 44 because we also have another r3 allele in there. For the next one, we only have r3 alleles in it, so we're going to have 11 times 2. So that each of those are going to give us a number, right? So then we're going to take that number and divide it by the actual allele. So we get, on this side, we get 314 and then 66. And we're going to take that and we have 380 total alleles, and we're going to divide that by each of these. So our allele frequencies are going to be R2 equals 0.83, and then R3 equals 0.17. Okay, so from there, we're going to go and we're going to take these allele frequencies and we're going to plug them into our Hardy-Weinberg equation, p squared plus 2pq plus r squared, or q squared, sorry. And from there, we're going to get each of our different frequencies, our expected frequencies. So in each of those, so for that one, I would just multiply, I would square root this, right, for our p squared. It would give us a value. And then we take that value, which happens to be 0.689, and then we're going to multiply it by the total number of individuals we have. So we have 135 plus 44 plus 11, which gives us 190. And then we're going to multiply 6.689 by 190. And that's going to give us a number. That's going to give us our expected phenotype. From there, we're going to plug it into this equation. You guys remember this from an earlier chapter? And we're going to take each of those, so we're going to do that for each of them. So I'm going to get a frequency here, I'm going to get a genotype frequency here, I'm going to get a genotype frequency here. And I'm going to plug it into this equation. So our observed is going to be this number up here. So we have 135 for this genotype, 44 for this genotype, and then 11 for this genotype. And we're going to plug it into here, and we're going to get a chi-squared value, which happens to be 7.4. So then that's going to tell us if it lies in the lightly shaded region, it's going to be within the Hardy-Weinberg equilibrium. If it's outside of it, it's not going to be inside the Hardy-Weinberg equilibrium. And since this is outside of it, it's not going to be in it. So for the last question, we're going to use a similar type. Of thing here. We're going to try to So we're going to use a type of equation like this, but since we have multiple genotypes, it's going to be a little bit different. So this is our Hardy-Weinberg, just an example of the Hardy-Weinberg equilibrium equation. But instead of that, we're going to just take so it asks you for the different frequencies of each one. So for CCH, and then so for the CCH, each of the frequencies are 0.37. We're going to multiply those together. And then that's going to give you an equilibrium. So for this one, it's going to give us 0.1369. So that's one of the things that it asks for on part A. That's just an example of how to do that. And you'll just continue that through with CB. You'll take CB times C, which is 0.25 times 0.15, and get 0.075, same kind of thing you did here. So that's for CH. Part B, what you're going to do is you're going to see, okay, you're going to look at, it asks for the pale gray phenotype. So then you're going to take CB, which is the pale gray phenotype, and C, and just ask for heterozygous, and go like this, 0.25, C times 0.15. And that's going to give you a frequency, genotype frequency. And from that frequency, you're going to take that and multiply it by the total number of individuals that it asks for, so for times 2,000. So take that number times 2,000, and that's going to give you the total amount, individuals, which is 150. Okay. And then for the next one, figure it out. It's the same type of thing. So you're going to look up here and ask for the amount of dogs that would have a white coat with dark eyes. So for this one, you're going to have 2 that give you this. So one of them is going to be the CB, and also the CDC, like that. And from there, you're going to do the same thing we did in the previous problem, except you're going to add these two together and then multiply it by the 5,000 dogs that it asked for. And then for the last one, it's the same type of situation. It says or, so you're just going to do the same thing. You're going to find, for the first one, it asks for C, CHB, CB. You're going to take those two allele frequencies and multiply them together. And then for the other one, you're going to see it says CC. So you're going to find those two allele frequencies, multiply them together. Multiply those each individually by 15,000, and then add the total number of dogs together that you got, and then round accordingly. So that's kind of it in a nutshell. We went a little over, but that's okay.